So the topic of the talk is acceleration of an incompressible image boundary-based CFD solver over multi-GPU platforms using OpenACC. I'm going to give a brief overview of image boundary solver because it might be little new to few of the audience. And then we'll see that what are the steps we followed up in accelerating over first to a single GPU, and then what we did it for multi-GPU parallelization. And we have used two different hybrid parallelization paradigm. One is MPI OpenACC, another is OpenMP OpenACC. Discuss on that. Then I'll show the performance metrics and some of the test results. And this work is mostly carried out by few of my PhD scholars, Mr. Nandan Sarkar, Devajyoti Kumar, and Siddharth Sharma. And Mr. Bharat Kumar Sharma, GPU advocate NVIDIA, has very closely monitored this work and helped us in different aspects. Immerse boundary method is one of the approach in CFD simulation in which flow over moving and deformable geometry can be computed using a general Cartesian mesh bracket. So in the background, we use a structured Cartesian mesh without considering the movement and complexities of the geometry. Now the difficulty in that how to impose the boundary conditions. In order to do that, we identify the complex moving deformable boundary by a set of Lagrangian points, which are immersed inside the Cartesian mesh. Then we see that which are the Cartesian mesh blocks, or what are the nearest Cartesian points of Cartesian mesh points of that unstructured set of points defining the Lagrangian solid boundary, and use a forcing function. This was first proposed by CSP scheme in simulation of flow over deforming hard walls. So what he has done, he has solved the blood flow over the entire geometry without considering the effect of, without considering the geometric effects during mesh generation for the hard walls, and then found out what are the fluid points which are close to the hard wall, and obtain what should be the force on the hard wall due to the deformation which is given by the blood on the fluid on the hard wall, and the equal and opposite force should be given on the blood. And then he calculated that what should be the flow force on the blood adjacent to the hard wall, and then distributed it using a Gaussian function to the nearby fluid points. In that way, the need of directly imposing the boundary condition is eliminated, and flow can be solved using a simple Cartesian mesh framework. So the effect of hard wall is not considered exactly through the mesh conforming boundaries, rather than boundary condition coming from the force given on the blood fluid. In our implementation, what we have done, that we have defined the immersed surface. This is an example of a turbine blade rotating inside a fluid domain. We have identified the moving turbine blade surface by a set of Lagrangian points, triangular elements, and then we identified which of the fluid cells are being intercepted by this set of mesh points at one particular point. We have identified points in categorized points in three directions through this search. One is that what are the immersed points, what are the fluid mesh points, which points belongs to the fluid domain and which points belong to the solid domain, and what are the cells which is being intercepted by the fluid domain. We identified those points and used a polynomial interpolation, second order polynomial interpolation, to explicitly set the velocity so that it satisfies the boundary condition over the surface while satisfies the outer domain fluid conditions, which is coming from solving of the equations. Now, if we see, there are that we have applied successfully this method into several problems like moving wings, oscillating fins, continuous casting problem, biofluidics, deformable arteries, etc., in several problems in complex and moving geometries, and we have used a fixed Cartesian mesh in the background. If we see and there are validations, verifications, etc., which has been extensively done. If we see what are the main computational challenges in this method, there are three particular issues in which we have to focus. One is that when we are solving incompressible Navier-Stokes equation, we solve a pressure correction equation here using Markov-Cell method. If there are n by n mesh points, the effort for solving this pressure correction is of the order of n cubed. So when we talk about few millions or hundreds of millions of mesh points, overall pressure correction is very computationally complex part. Another part is searching for the intercepted cells. There are around 100,000 surface mesh points in a few million volume cell background. So we need to identify which of the volume cells are intercepted by the surface points. So that includes a complex search point algorithm. And then we have to interpolate the velocity, pressure, etc. at the force point, which also requires certain effort. We can see that 73% time in a general implementation, 73% time is taken by Poisson equation, 13% time is taken by surface tracking, and 5.6% is taken by momentum equation. So when we went for OpenACC parallelization for multi-core and GPU systems, especially we'll talk about GPU systems here, then we tried to primarily focus on these few hotspots and tried to parallelize that. So what we have seen that Poisson equation has to be parallelized. There are many Poisson equation solver. Among them, the explicit one is Jacobi solver, which can be very easily parallelized. However, it has a very slow convergence. Surface boundary conditions, there are difficulty in parallelizations, especially because we need to use certain if-else loop in order to find out which of the surfaces are intercepted, and then we have to apply the boundary conditions there. It can give us warp divergence. And then when we have to reconstruct the parameters, interpolate the velocities, there will be memory overheads associated. Along with the Poisson equation, we are solving an extra constant equation for mass conservation. We observed that this has certain data dependency in the solar constant equation, and it is difficult to parallelize, especially if we go for large scale CFD problems. In GPU systems, it requires a lot of updates, and it has certain data dependency also. So we dropped this term and used a different interpolation strategy in which we can overcome this. So after doing this parallelization, we can see that initially where 71%, this is another implementation where 71% time was being taken by CPUs. It is in GPU, it is taking 67% time. However, there is nearly 200 times speed up in the Poisson equation solver. There is also substantial speed up in some of the other components like surface tracking, boundary condition implementation, etc. However, there is a memory host to device memory copying time. And overall, as we increase the mesh size, we start getting very good speed up in GPUs after the baseline OpenACC acceleration. And in 26 million mesh points for an arterial flow problem, we get around 139x speed up in Tesla V100 GPU compared to Intel SKL CPUs. Now we look into some of the algorithm modifications which can further optimize it. That we have seen that a red-black successive over relaxation technique can remove the warp divergence and give faster convergence than the Jacobi. And then instead of using if-else condition to find fluid, intercepted, and solid cells, we have grouped them and put them into one data structure. We have used something called a compressed diagonal storage matrix, which I'm going to show in the next slides. Remove the SOLA, used field extension method. Simplified the reconstruction scheme using one-point interpolation. Instead of finding out more than one interpolation points in the fluid domain, we found out we used one interpolation point and used the derivatives of the velocity along with the primary variable. And dynamic allocation and creating and destroying arrays, that also helped us. So this is one idea, that we identified the solid points, intercepted points, and fluid points separately and group them and use pointers for each group, which remove the warp divergence part. And then what we can see that when we are using a structured Cartesian mesh, the coefficients, in the matrix coefficients, off diagonal coefficients are same along the entire y direction, along the entire x direction, and along the entire z direction. So instead of using a simple diagonal storage which requires 7 data points for each row, we only stored the x direction, y direction, and z directional elements for each of the lines, and that reduced the memory requirement significantly from n square to n in a or of the order of n square or n. In a 2D problem, it reduces the memory requirement by n times, and in 3D it required by n square time. And through that, the red black SOR that we have formulated that required a very small amount of memory, around 0.597 memory, whereas the CSR or diagonal storage required 5.12 gigabyte memory. This is for one particular example. So when we use some of the optimized solver packages, we actually encounter more memory. Rather, our in-house code with this diagonal storage can work with lesser memory requirement. And then we can see that after this optimization, as we increase the mesh, we get nearly constant speed up with the previous unoptimized method and the new optimized method. Around 1.8 times speed up is obtained. We have seen a 16 million cell problem of flow over a sphere, and then we have used the memory requirement is reduced by fetching operation, and then we have eliminated the update loop using pointers, and we can see that we can substantially reduce the computational time for the Poisson equation compared to the previous one. And then we can see that for 16 million problem, earlier we are getting 178 x speed up, and now in A100 GPU we are getting 336 x speed up. So nearly 1.8 to 1.9 x speed up is obtained without compromising with the accuracy. We have shown the validation results, comparison of our results with benchmark solutions here. For internal flow, that was for external flow cases. For internal flow, you are also getting good speed up, and when we compare our solution with AMGX, which is a GPU optimized solver library, but it uses a CSR format, so it uses larger memory. We can see that we can use 1/3 of the memory, as well as because we use less memory and we can reduce the number of operations through this compressed storage algorithm. The time per iteration has also substantially reduced. It's almost half of AMGX in our successive over relaxation method. However, for external flow, where more points are, where the boundary conditions are more Neumann in nature, the matrix is stiffer, we get AMGX works comparable, or we get slightly better speed up in AMGX. But memory requirement is more even if you use solver package than our in-house compressed diagonal storage based code. And then we have also optimized the surface tracking algorithm. This is important because if we do the tracking, this is done only once for a fixed geometry, but when we have a moving geometry like this heart valve example, at different locations of the different instance of the movement of the heart valve, this is the closing of the valve and again the valve is open, we have to iteratively keep on tracking the geometry and find out which is the surface, which is the intercepted cell, which is the solid cell, which is the fluid cell. Instead of tracking for each of the fluid points, if we use a tracking based on the solid surface points using a bounding box, we can reduce the computational time further by 8.6 times. And this is more GPU friendly search algorithm. So after that, we thought of parallelizing it into multi-GPU systems. So we have GPU nodes with 2 GPUs per node. So we thought the easiest way will be using an OpenMP running 2 threads each for two of the GPUs, and then each thread will take part of the domain or part of the matrix and solve that in GPU. And we use this red-black coloring to remove data dependency and warp divergence, and we can see that there is a good speed up. However, for single to multiple CPU, we are going for 2 CPUs, there is around 1.2 times speed up, but from single to multi GPU, there is around 1.6 times of speed up. Little reduction in speed up due to OpenMP synchronization, etc. And at one particular case, the speed up is also not linearly increasing with mesh size, because we believe that there are cache related issues when we implement OpenMP parallelization. Next idea, and then we solved direct numerical simulation of lead-driven cavity at 10,000 Reynolds number and resolved all the turbulence scales, etc. Then we took this into a multi-GPU MPI system, and we have used a asynchronous communication and used a particular optimized GPU assignment ring topology for pinning different grid blocks to different GPUs, and we can see that we have done certain things like decomposing in one particular direction, which is more cache friendly, and asynchronous data transfer, which reduce the computational time in general. And we can see that when we go to 4 GPUs for large mesh problem, we get nearly 4 times speed up compared to the single GPU implementation for Poisson equation as well as for pipe flow using IBM. And the speed up also depends on the GPU architecture. DGX works better than PCI based GPU connections, and we can get better speed up. Even up to 16 GPUs, we can get almost linear speed up there. We took this problem to solve biological flow in stenosed arterial wall, and we can see that in DGX system with nearly 60 million cells, we got around 6.3 times speed up, and the relative A100 to V100 performance is around 1.5 times. So A100 performs 1.5 times faster than V100, and we have chosen a 300 million cell problem for flow over 3D wing, and we observed that it scales linearly speed up in 8 GPUs with number of GPUs, and found out vortex structures are different. They are different angle of attack Reynolds number, etc. We have compared the multi-GPU implementation with respect to AMGX with our RBSOR based in-house code implementation, and we saw that for multi-GPUs our solver is faster than GPUs, and as we increase the mesh size, we can see better speed up. So in summary, I'm showing an immersed boundary solver for incompressible flow simulation over moving bodies, OpenACC based parallelization of the solver, and relevant optimization steps I've discussed. We have discussed multi-GPU implementation using both OpenMP and MPI, so both shared and distributed memory, and then presented several test case results. Thank you for your attention.